So we just spent some time talking about the D flip-flop, which we have determined is a better sequential circuit than an SR latch because it is edge sensitive rather than level sensitive. But it comes at the price of having more circuit elements involved in it. So a D flip-flop is our most basic memory element in a digital circuit. So how do we model a D flip-flop in VHDL? Well, if we recall, the inputs to a D flip-flop are D and clock, and your output is Q. You could also have a Q0 output, but in this case, in our entity description, we're going to define D and clock as standard logic inputs and Q as our standard logic output. And if you also recall, the equation for the D flip-flop, its output Q next, is going to just get whatever D is. Alright, so let's look at our architecture definition for the D flip-flop. Here we have the architecture, my D flip-flop of D flip-flop is, and we're going to put this in a process statement because we want to use the if construct. So in the process, in our sensitivity list, we want this to change when D or clock changes. So we put those in the sensitivity list. Now here we go. If rising edge of clock then. So rising edge of clock is referring to the transition from low to high of the clock signal, which means we're going to only evaluate this circuit on the rising edge of the clock. So if you remember from our timing diagram, right here, we're evaluating only at a rising edge of the clock. So you can write that in just like that in VHDL. If rising edge of clock, then Q gets D. So this is where Q is going to get whatever D is. So our next state Q will be D. Now look here, this if statement has no else. So you're wondering, well, if rising edge of clock, then this, else what? Well, having no else is how VHDL simulates memory, or induces memory in the circuit, I should say. So else what? Well, else just hold whatever you have. So if it's not the rising edge of the clock, you have to remember your current state of Q. So if rising edge of clock, you'll reevaluate and Q will get whatever D is. Else, you're just going to stay where you are. You're going to remember your current state. So you leave off that else to imply the memory in the circuit. So you end your if, you end your process, and you end your architecture. So this is how you model a D flip-flop and model a very basic memory element in VHDL. So what more can we do with D flip-flops? Well, D flip-flops can have both synchronous and asynchronous reset or set conditions. Meaning, like, what if we wanted to, in the middle of our circuit, reset to the 0 state, or maybe set to the 1 state? Well, we can have another signal that does this, and it could be synchronous or asynchronous. So let's look at what that means. Here's an example of a D flip-flop with an R input, which is going to be an active low asynchronous input that clears the D flip-flop outputs when asserted. Alright, so what does that mean? So in this model we have a D input, an R input, clock input, and then Q and Q0. So R is asynchronous. Asynchronous means that it happens outside of the clock, so it does not depend on the clock edge. That means whenever that signal is deasserted or active low, we're going to change the output to 0. So if you look at a model of this in VHDL, here's how you would model an asynchronous reset condition that is active low. Alright, so here we have our inputs for our entity, D, R, and clock, which are inputs of type standard logic, and the output Q. Now the architecture, my DFF, I guess this NR stands for reset of this DFF, is, again, we have a process statement with D, R, and clock in our sensitivity list, because whenever one of these changes we want to reevaluate. So if R equals 0, remember this is an active low reset, then Q gets 0. So this is how we input the asynchronous active low reset. Notice that this if statement happens outside of the rising edge of clock statement, which means we're not dependent on the clock, which makes it asynchronous. So if R is 0, then Q gets 0. Else if rising edge of clock, now we're depending on the clock, then Q gets D. Again, there's no else, which means else just hold whatever you have. And if. So if you had a synchronous reset, this if condition is going to go inside the rising edge of clock condition. And we'll take a look at that next. Oh, actually, this is great. A timing diagram for this asynchronous reset. So here's your clock signal. Clock is just going up and down. Remember that we have a positively triggered flip-flop, which means that we're going to evaluate on the rising edge of the clock. And we have an asynchronous active low reset. Okay, so the reset is 0 here, which means Q is 0. And Q will then hold itself until the rising edge of the clock. At the rising edge of the clock, Q gets whatever D is. D is a 1, so Q becomes a 1. Q stays a 1. Notice that reset is not 0, and we don't evaluate what D is until the next edge of the clock. So here we have another edge of the clock, and we have D is 1. So Q stays 1. Now we have a 0 on the reset, and because it's an asynchronous reset, that means that even though this is not a clock edge, we still evaluate it. So Q drops to 0 at this point, and it holds to 0 until the next edge when we need to reevaluate what D is. So D is 0 at this edge, so Q stays 0. We hold it until the next clock edge. Notice there's no reset condition that happens here. And so the next clock edge, D is still 0, so Q stays 0. And we evaluate now at the next clock edge, D is 1, so Q becomes a 1, and then reset drops, so Q drops, and then holds until the next edge. So once again, the asynchronous reset means you evaluate the reset whenever it happens. It doesn't have to happen on the clock edge. But you evaluate D gets Q only at the clock edge. Let's look at one more. We have now write the VHDL code that describes a D flip-flop shown on the right. Use a behavioral model in your description. Consider the S input to be an active low synchronous input that sets the D flip-flop when asserted. So now this is going to be a synchronous input, so it has to go inside the rising edge of clock description. Okay, so our inputs are going to be S, D, and clock, and our output is going to be Q. Let's see how that looks in VHDL. So here we have DS and clock as our inputs. Our output is Q. Our architecture now starts with if rising edge of clock, then. So if rising edge of clock, then if S is 0, here is our synchronous set input. It's synchronous because it happens inside the rising edge of clock block. So if S is 0, then Q gets 1. So this is our synchronous active low set condition. So if that's not the case, else Q gets D, and if. For this if, and if for that if, and process for this process, and then end for the architecture. So this is how we're going to model the synchronous active low set input. Let's look at a timing diagram of how this would look. So now we have our clock, D, S, and Q, and we evaluate the Q at the rising edge of clock, and we also evaluate the set at the rising edge of clock because it is a synchronous set signal. Alright, so here we're assuming that Q starts at 0 at the rising edge of clock. We see what is set. Set is not 0, so it doesn't matter. Remember, it's active low. So we look at D. D is 0, so Q gets D. Now we traverse along. Oh, look, set is dipping here, but we don't evaluate it because, remember, the set signal is synchronous, so we can only evaluate it at the clock edge. Okay, so we move along, and at this clock edge, We look at what set is. Set is not 0, so we don't need to worry about it. So we use whatever D is. D is 1, so Q gets 1. We hold 1 till the next clock edge. Again, first look at set. It's not 0, so we look at D. D is 0, so Q gets 0. Hold on to the next clock edge. We look at set. Set is not 0, so we look at D. D is 0, so Q gets 0. Now, again, clock edge, we look at set. Oh, look, set is 0, so that means no matter what D is, we're going to set this. So at this edge, we're going to set, which means bring Q to be a 1, and now Q is a 1.